second lecture by Clifford.
Cool. So why don't we get started? So I'm going to pick up basically where we left off last time, but I'm going to maybe slow down a little bit and make sure that we're kind of all on board whenever I say things. So please, if you have any questions, the best way to slow it down is just to ask them. So if you have a confusion, just ask me in real time. It's the more questions, the better. Just to recap, like what we were doing. So I had told you that there is a way to construct scattering amplitudes that don't use any of the machinery of quantum field theory, like Lagrangians or Feynman diagrams, where instead the kind of the kind of basic procedure is to write down a space of functions. So by space of functions, I mean an amplitude depends on kinematics, like momenta, say, or polarizations, or whatever your particular kinematic variables are. And what you should do is literally write a function of all possible things that your amplitude could be, and then you enforce constraints. What we were doing last time was to show kind of the basic version of that bootstrap picture, where we studied first scalars. Okay, so what did we do for scalars? For scalars, we just wrote down the 3-particle, 4-particle, and so on scattering amplitudes, which were just functions of pi.pj, which were the momenta. Okay, and then we found that it was a way of classifying theories. There was always a correspondence between the amplitudes we could write down and Lagrangian operators. That wasn't super surprising, but it was a kind of a lead-in to what we'll do here, where we'll learn some slightly more non-trivial things. For the case of vectors, again, to maybe slow down slightly, we had a definition of momenta, pi mu, where mu is the Lorentz index and I labels particles. So p1, p2, p3 are the momenta of legs 1, 2, and 3 for a 3-particle amplitude, and so on. And we also had a polarization, ei mu. Okay. As I said before, this usually has some backstory coming from QFT. But the idea of this kind of version of a bootstrap is to write all possible Lorentz invariants or inner dot products of these objects, and then to impose the Ward identity to obtain some consistent amplitude, where the Ward identity tells us that if we take any polarization and we send it to pi, okay, so take any external polarization for like leg 7, take E7 and send it to P7, then the amplitude should vanish. This is the statement of the Ward identity. What this does famously from your QFT textbook is it removes the unphysical degrees of freedom inside the polarization. The photon has 2 helicities. A 4 vector has 4 degrees of freedom, so we need to start removing degrees of freedom, and this partly fixes that. Okay, so operationally, again, what did we do for the vectors? I mentioned this feature of what's called a minimal kinematic basis. Let me state it again, just to be explicit. Naively, you would build all possible inner products of E's and P's. Okay, E's and P's, E1.E2, E1.P2, whatever you want. Okay, but we had a set of on-shell conditions, which was the statement that P1 squared equals P2 squared equals P3 squared equals 0. Okay, in addition to P1, E1 equals P2, E2 equals P3, E3 equals 0. Okay, and the idea was we wanted to pick variables that trivially encoded these automatically. Okay, so in other words, eliminate these constraints by imposing them on the general space of invariants you could build. Okay, so maybe hyper concretely, okay, we can eliminate P3 everywhere by writing it as minus P1 minus P2. Okay, so in other words, all invariants that involve P3 we will drop because we can write them in terms of P1 and P2. On top of that, we can use nice identities like this. So P2.E3, okay, nominally this is not independent from P1E3. Okay, why is that? The reason for this is that P1 plus P2 is P3, and P3.E3 is 0. So I can relate these. These are not independent. Okay, so the idea here is write down every possible dot product, and then remove everything that can be eliminated with equations like this. Now, there's many ways to do that. I could choose to eliminate P2.E3 or P1.E3. You could do it a million different ways. It doesn't matter which way you do it. Just pick a basis. Okay? The point is, though, once you enforce these conditions, you get what's called a minimal kinematic basis, which is the minimal basis of these dot products, these invariants, where everything is on shell, no matter what values these take. Okay, so the idea is I'm thinking of these dot products as kind of independent variables. Okay, this could be like x, y, z, w. These are just like whatever values you want them to take. The point is you can set them to any value you like, and because you've already eliminated everything else with respect to them, you are on shell. Okay, this is a way of writing down a function which never dares to be not on shell. It's never accidentally off shell. As soon as you become accidentally off shell, your quantity is not physical. It has gauge redundancy, gauge fixing, field basis, dependence, all in it. So all those things I told you last time, which evaporate in physical processes, they would come back to life if you don't do this correctly. Okay. All right. So the point now is we want to write down an amplitude that just depends on these in any way possible. As I said, x, y, z, just write a function, a polynomial if you like, in all these variables, and then demand constraints. Okay? So for the case of vector theories, okay, again, maybe I'll say this again. We know that when we have, let's say, a 3-particle amplitude of 3 vectors, okay, so the external legs are vectors. Each vector is labeled by a vector polarization, okay? Why is that? That's because when we talk about linearized solutions to equations of motion, so if this was like a mu of x, we would write this as some e mu e to the ipx, okay? This is hopefully familiar from your QFT textbooks, okay? So that's why each of those external vectors comes with one polarization. There's an E1 for leg 1, and E2 for leg 2, and E2, E3 for leg 3, which means, as usual, you should get something that looks like what we structurally see from Feynman rules, which is 3 polarization tensors, E1, E2, E3, mu nu rho sigma, times some object, mu nu rho sigma, okay? I'm just saying it's multilinear in the polarizations, and all the hard work of a Feynman diagram is usually computing this thing. Now, the second way of writing this is to just say, imagine taking all these dot products and just writing out all possible space of functions that these can be, and that's what led us to our first ansatz for a scattering amplitude, which is really what I left off with last time, which was, let me again write it out just to be super explicit and maybe even redundant, which is C1, E1, E2, P1, E2, plus C2, E1, E2, P1, E3, plus one last coefficient, C3, E2, E3, times P2, E1. Okay, so every object here is in this minimal basis set. C1, C2, C3 are just constants. They're just like literal numbers, which are unfixed. Okay, and we're going to fix them by imposing the word identity. Okay, any questions about that? Okay. So good. Again, maybe just to, even if you don't have questions, I'm just going to say it again. E1, E2, and E3 all show up at least one time. Sorry, this should be an E3. E1, sorry, this should be an E3 and this should be an E1, E2. Okay, some typos there. E1, E2, E3 show up once in every term. And the assumption here was some power counting, which was this amplitude scales as exactly 1 power of p. We're going to go up in momentum. You can go to p, higher orders than p. We'll see what happens. But for the lowest order you could possibly ever have, it's 1 power of momenta, and this is all that's allowed. Okay. Now, what did we fix? We imposed the word identity, which I just said, but let me just say it. Let me show you for one example what that is. Take E1 and send it to P1, and just like take E1 and plug in P1 into this expression, and you get lots of terms. What do you get? You get things that look like this. C1 plus C2 times P1 E2 P1 E3. This is the kind of expression you get. Okay. Now the point is, so I've gone back to a minimal basis here. The point here is that this thing has to be 0, so this is 0, which means C1 is equals minus C2. Okay. So I've fixed. Good question. Yes. Oh, why did we assume it's a rational polynomial? That's a great question. So here, I've implicitly assumed that there's no singularities in the three-particle amplitude. So I don't want any 1 over momenta, because the three-particle amplitude is not something that should factorize into anything lower point. 3-point is like primordial, right? If I was at 4-point, I could be like, oh, there's a 1 on S. But at 3-point, it's just a vertex. So that's why there's nothing in the denominator, and that leaves only polynomials. Yeah, that's a great question. Yeah. Any other questions or clarifications? Yes. Very good. So again, I could go through 2 and 3, but I think you get the point. You'll get other equations when you set E2 to P2, E3 to P3. And what that does is it sets your coefficient C to be a very particular combination, which as I said last time, is that they are proportional to 1, minus 1, minus 1. Okay? So in other words, up to an overall normalization, which will never be fixed by this procedure, because I could always multiply everything by an overall constant. This is the relationship between coefficients. Okay. Now, then it is just algebra. I just leave algebra to you, which is when you plug in those coefficients 1, minus 1, minus 1, and just arrange terms, okay? Reshuffle them. We found that this three-particle amplitude had a nearly complete form representation that looked just like the vertex in Yang-Mills theory, the 3-gluon vertex in Yang-Mills theory. It looked like E1, E2 times P1, E3 minus P2, E3 plus cyclic permutations. Okay, so what do I mean by that? So I just mean clocking 1, 2, and 3. That's what cyclic here means. So the idea is send 1, 2, and 3 to 2, 3, and 1. And then another term, which is sending 1, 2, and 3 to 3, 1, and 2. Okay, so whenever I say cyclic permutations, I just mean take the external legs and permute them by the cyclic group. Okay, cyclic group on the number of external particles. Okay, so there's 3 terms here corresponding to 1, 2, 3, 2, 3, 1, 3, 1, 2, all of the same structure. Okay, good. So that's what we saw last time. And the immediate issue was that this is anti-symmetric in swapping 1 and 2, which you can see because these 2 permutations are automatically symmetric in 1 and 2 because they're swapping 1 and 2. Here, it's anti-symmetric in 1 and 2 because I have a difference here. So if you just write this thing out, you'll realize it's anti-symmetric in swapping any pair. 1, 2, 2, 3, or 3, 1. You get a minus sign. Why did that not make sense? Well, scattering amplitudes signify actual particles interacting. It's like, if you like, a bunch of in and out states being contracted. And if you swap the momentum labels, you are swapping particles, right, in quantum mechanics. You take 2 particles and swap their positions, then you're swapping 2 particles. If those particles are identical, if they're exactly the same particle, then they're either a boson or fermion, which means you get a minus 1 or a plus 1. And these were vectors, so we assumed from the Bose statistics that this vector should be a boson. Okay? That is definitely an input, which I'm not going to be proving. And there's no claim that amplitudes would give you that information separately. You still need to know some things about quantum mechanics. But we're going to take that as input, which tells us that this is actually inconsistent and is 0, unless we add a twist. And this is what I left with last time, which was we add. So it is true. It is a true fact that 3 vectors cannot couple cubically. It is impossible. The same vector cannot couple cubically. The point, though, is when we talk about gluons or W bosons or what have you, those are not the same. Those are not the same vector boson. They're different ones. W plus W minus Z, or red, green. Different gluons in the adjoint of SU3, and the nice little caveat, which conveniently allows gluons to exist, is that we put a structure constant here. Okay. And again, this is something you should know from QFT, but the structure constant is kind of the very first thing that you introduce in the gauge theory, which defines the gauge group. Okay, it's fully anti-symmetric. It's usually given to you from on high, but here we realize it's entirely mandated by nothing more than constructing Lorentz invariance, an object that's order p to the 1. Okay, so this is Yang-Mills. So first fact we've learned. there is only one theory of interacting vectors that goes at this order p to the 1. It's only one, Yang-Mills. Okay, so if your friend says, I found a second theory that has 3 vectors, they interact, and it goes as order p to the 1, you can already know that it either isn't Lorentz invariant, isn't consistent, or secretly isn't Bose-symmetric. It's somehow coupling very distinct objects. Okay. Good. Now is there any questions about that? Okay. Now let's move on to p cubed. Okay, so what do I mean by order p cubed? It's exactly the same operation. Okay, we go to 2 more momenta. I have to add pairs of momenta because to keep Lorentz invariance, I need an even number of Lorentz indices. So I have to add 2 more momenta. And now the idea is we can now write another ansatz for this case, which just has linear in E1, linear in E2, linear in E3, and 3 p's. Okay, just write every possible function of that form. Okay, what is that space of functions? Well, you should first keep in mind that the p can't dot with another p. P1 dot P2 is 0, remember? Because we're talking, I should say, well, it's implicit here, a massless vector. Okay, so P1 dot P2 isn't in this minimal basis, like noticeably, just kind of re-emphasizing that. That means the only thing you can write down with 3 p's is actually P1 E2, so P dotted into an E, another P dotted into another E, and another P dotted into another E. So this is P1 E3, P2 E1 times some coefficient. Okay. So in other words, if you arrange this in any other way with 3 p's, then 2 of the p's will contract with themselves and be 0. So that I'm not caring about 0, so this is the one object. As it turns out, again, you can rearrange this in a more familiar form. This is exactly equal to the following expression. Okay, let me first write down what it is, and then I'll explain what it means. So F2 new row, F3 row mu. Okay, where Fi has the labels of a field strength because it's actually the linearized field strength, like gauge field strength, quote unquote, for one of the external legs. So concretely, I mean, this is just shorthand for Pi, EI, mu, nu, anti-symmetrized. Okay, so like if you were in like QED in Maxwell theory, this is what you'd call the field strength. Of course, we're not in QED. This is going to be something which is more non-abelian. But this is the linearized field strength. It's the first term. Okay. Any questions about what? This is just a symbol for more momenta and polarizations. Yes. Sorry. Well, I haven't gotten to that yet. I'm about to get there. Yeah, I'm about to get there. Yeah. What is the round bracket square bracket? I'm sorry, this is just a poorly made square bracket. Yes, this is an anti-symmetrization on mu nu. Yeah, sorry, I was just really poorly written. Thank you. Okay, I will get to the coupling constant in a second. Okay. But the point here is this is the product of 3 field strengths. Okay, this is also usually known as F cubed. You write this as a kind of F cubed operator in a theory. You'll notice, though, it's also antisymmetric in swapping 1 and 2, swapping 2 and 3, and swapping 3 and 1. Why is it antisymmetric? Well, F mu nu is an antisymmetric matrix because it's manifestly antisymmetrized in mu nu. It's a product of 3 antisymmetric matrices with a trace on it, which means if I swap any 1 and 2, I get a minus sign. Any 2 matrices here, I get a minus sign. Okay, so this is antisymmetric in swap, just like this lower point piece was, which means that again, if these are 3 identical vectors, it's 0. Okay, so this is also ruled out for the photon. The photon cannot couple through this. What I do is the same trick as here before, which is I write down a structure constant. Okay, now I'm calling it the same FA1, A2, A3, but in principle, there's not necessarily a relation to these yet. Okay, we haven't deduced that yet, but I'm still going to call it this because we know that we should be identifying in the end with the operator F cubed in Yang-Mills theory. So in Yang-Mills theory, of course, the usual Yang-Mills Lagrangian is the F squared piece, which is where F is the non-abelian field strength. Here by F cubed, I mean I'm saying this thing is in the Lagrangian. The Lagrangian contains this. In fact, let me Let me just be very hyper explicit. There's a Lagrangian. Normally we write something like 1 over 2g squared trace f squared. Okay, this is the Yang-Mills Lagrangian. Hopefully very familiar to you all. Okay, but we can add higher dimension corrections. Okay, so in the standard model effective field theory, this is known as the anomalous cubic gluon vertex. It's just some f cubed trace divided by a cutoff. Okay. So it has a different dimensionality of coupling than the leading piece. There's of course a whole train in principle of other higher dimension operators, but the leading piece that you can write down, which is gauge invariant, is f cubed. Okay, where this f cubed is the full non-abelian gauge field strength. Okay, so this is the Lagrangian picture. The associated three-point vertex is this. Okay. So what have we learned? We've learned that now there are two types of interactions that a vector can have, or I should say a bunch of vectors because they need to have some index here. One is the minimal Yang-Mills three-point vertex. The other is the leading correction to that, which is the f cubed anomalous gauge boson cubic vertex. Okay, trilinear coupling. Any questions about that? Yes. Yeah. Yes. Debye mass, your degrees of freedom will look different. I don't know anyone who's actually tried studying that from a bottom-up bootstrap. But I personally have considered something which is maybe tangentially related, which is that relatively famously, if you think about fluid dynamics, it has many very close similarities to a gauge theory. The kind of classic example being if I had some velocity field, three-dimensional velocity field that is solenoidal. Okay, so like incompressible fluid dynamics. There's some kind of divergence of velocity field vanishing, which is very reminiscent of kind of Lorentz gauge in the gauge theory. It has a sense in which there's helicities, and you can bootstrap amplitudes like of fluid quanta that way. In terms of being at finite temperature, I don't know anyone who studied it, and I think it's really just a question of attention. If you were working in a theory that's at finite temperature, you've compactified time, I think all the same principles would be here. You just have to, again, find the right variables to describe it. And keep in mind that the less symmetry you have, the more freedom you will get. It's kind of obvious. If I broke Lorentz symmetry, I wouldn't just have these 4 vector inner products, I'd have 3 vector inner products in addition to energies. And I can just write down more objects. That's what you literally find. Like the space of objects that are allowed grows. Conversely, if I add more symmetry, like I say, I don't just want Poincaré, Lorentz Poincaré, I also want conformal symmetry, then of course it's even more constraining. Okay, so you can go both ways, but the less symmetry there is, just the more variety of structures you'll have. Said another way, the more coupling constants you have. So we have discovered 2 independent kinematic structures. This corresponds to 2 Wilson coefficients in the action. And that's just a general feature. Yeah, thanks for that question. Any other questions? Okay, good. Now we can keep going. And thankfully, there's not farther to go for vectors. Why? Well, there's not much to say here, but let's say I wanted to go to p to the 5th or higher. Well, I know that I'm done. Why am I done? In other words, I know that these are all 0. Okay, without doing any logic, without doing anything fancy. Why is that? I have 3 polarization vectors, E1, E2, E3. That's 3 free indices. But I'm giving you here 5 momenta, which is 5 indices. So even if I soak up as many as I can into those polarizations, some of these p's need to dot into themselves, no matter what. This is the fact. I was okay with p3 because I dotted 1 into each polarization. But now I have more p's than e's, which means some of the p's are dotting, and pi.pj is 0 at 3 point, which means that this is 0, which means that there is no other 3-particle amplitude in Yang-Mills. Okay? Now, again, this is returning to what I've said in the past. You could say, wait a minute, that can't be right. I could put box to the 58th power f cubed. Okay, this is my favorite vertex. Okay, and of course, what I say is that is an illusion. There is a field basis where you just remove this entirely from 3-point and is actually higher point. So you didn't write a 3-point vertex. You secretly wrote a 4-point or higher vertex. In terms of the real physics, it really means we have now completely exhausted the space of all 3-particle amplitudes. There's only 2 for these vectors. Yang-Mills, and F cubed. Okay. Hopefully this somewhat demystifies the magic. Sometimes we're told like gauge theories, what a beautiful principle, this and that. At least this is conveying, at least in part, like there wasn't like a second way. There wasn't another option. Effective field theory and gauge symmetry were both required. All right, any questions about that? All right, now we can upgrade and see something a little more, again, hopefully slightly more interesting, which is the tensor case. The case of spin 2, not spin 1 vector, but spin 2 tensor. And it's going to be basically very similar. But I think maybe I'll acknowledge that you probably are maybe less used to thinking about scattering gravitons. So I'm using the word gravitons, even though we haven't yet figured them out yet. Okay, the idea is to bootstrap this, but secretly in our minds, just like vectors were gluons in the end, we're going to learn that tensors are gravitons, kind of obviously. At least you can see sociologic from the way I'm presenting it. Of course, for the graviton, we have momenta, but the polarization structure is different. Okay, why is that? So for the graviton, and again, if you have maybe offline, I'm happy to answer questions about graviton field theory. Okay, so maybe this deserves its own discussion. Let me just mention it because it's just so we're not all lost. I said this before, but you can write the action for gravity. You've hopefully all seen this, where this is the Einstein-Hilbert term, also known as just like general relativity. Okay, where this depends also on the metric g. And I went kind of very quickly by writing something that looked like take g and expand about some fluctuation, h mu nu. Okay. So kind of colloquially, this is known as the effective field theory of gravitons. And this is an effective field theory that you can study like any other effective field theory, like SMEFT. I think maybe this was emphasized in some previous lectures, maybe by Adam. But this is like no different from the chiral Lagrangian of pions. It's no different from higher derivative corrections in the standard model. And the point is, even though it is not renormalizable, you can still compute in it as long as you keep track of your power counting. On top of that, you can even compute quantum corrections. Okay, so let me just say this because it's probably important to hear if you haven't heard it. Sometimes folks will be very glib that gravity and quantum mechanics are inconsistent, like there's some craziness that makes them so incompatible that we'll never talk about both at the same time. Obviously, that is false at a practical level. Why? We have experimentalists at CALTECH and other places who have laboratories on the planet Earth, and they measure quantum mechanics. They study quantum mechanics systems, and the Earth definitely has gravity acting on it. Okay, they're in their lab and they drop a coffee cup and it falls. Okay, so gravity's in play. They're measuring things quantum mechanically, but enough hell doesn't break loose. It's all fine. So what happened? Well, the point is, gravity and quantum mechanics are 100% consistent if you work in a low energy regime where you treat gravity like an effective field theory. So there is some sense in which gravity is quantum and fine, but small. Okay, just like in the chiral Lagrangian, you can compute loops. You can take pions, throw them in loops. Part of that is ultraviolet divergent and is absorbed into a Wilson coefficient, but part of it is calculable. Okay, that's why when people do chiral perturbation theory and they're looking at loops, like it's not just like completely random functions that they're coming up with and then throwing away because it's ultraviolet divergent. The fact that it's not renormalizable is irrelevant. Okay, you just have to power count correctly and then renormalize. Okay, so hopefully that's generally understood as the modern understanding of why non-renormalizability should not scare you in the least. In fact, as effective field theorists, we do it like constantly, and there's predictions. So I'll even mention, you can compute something which is not ultraviolet sensitive in this effective field theory of gravity, which you can in principle measure in an experiment, and is completely independent of whether it's string theory or loop quantum gravity or whatever your UV completion you think might be. There are infrared, purely fixed by infrared quantum corrections in gravity. These were computed by Donahue using methods like 15 years ago, where it's not something absorbed in a counter term. It's something which is non-analytic and is physical. Okay, it's also extremely small and won't be measured in our lifetime, but it's calculable. Okay, so we shouldn't be scared of this because it's not UV complete. Okay? For the same reason that half the theories we talk about which are renormalizable, they aren't asymptotically free and they're also not UV complete. So that it typically doesn't bother us and it shouldn't bother us here either. We just have to be careful. Okay. Now in such a theory, there's a graviton. Is there any questions about what I just said? All right. Yes. Yes, I will sometimes do that, sometimes not do that. So yes, if you want to have properly normalized fields, you would write it this way. Sometimes it's actually nicer to not use normalized fields for various technical reasons, but it's up to you. Yeah, but indeed, here we would typically normalize this. This is just like in the chiral Lagrangian, where we normalize pi, the pion, with f pi. It's just like that. Okay, so the way to think about gravity is it's in so many ways just like pions. In pions, we have something that looks like u equals e to the I pi over f. Okay, so 1 on f is like 1 on m Planck. There's like so many similarities to them. Okay, their renormalizability structure and so on. They're both not complete. They both are pending a UV. They both have a UV completion that, in principle, could be many things. Okay, so there's a lot of nice continuity between those two. And in some ways, that's why pions, chiral Lagrangian, is the nice toy model for gravity, which has been known kind of forever. Okay, good. So returning to the gravity story. Okay, we have a graviton, just like for the case of the gauge theory. We can write h mu nu. And like our gravitational wave friends would say, we could write down a polarization for a linearized graviton. This polarization is naively, if you just wrote down something Lorentz invariant, you'd think it is a symmetric 4x4 matrix. Okay, symmetric 4x4 matrix has 10 degrees of freedom naively, but we know that's massively overcounting because a massless spin 2 particle, just like a massless spin 1 particle, could have 2 polarizations, the plus and cross polarizations for gravitational waves. So again, we still have that redundancy, but the point is if we build a scattering amplitude, it will depend on this epsilon mu nu. Okay, so the only difference to tensors is we have an epsilon mu nu. It's a symmetric epsilon mu nu here. Okay. Now I'm going to make do something that's really more out of convenience, but it's a great way of understanding the connection between gauge theory and gravity, which is in general, of course, I can take any symmetric tensor like this, and I can write it as an outer product of some set of other polarizations, like vector polarizations. Let's call this EI, EI. Okay, where this is summed on, let's say there's another index A. Okay, so this is me just saying that any symmetric matrix can be written as a sum over outer products of vectors. Okay, just the fact that if this is some rank 4 symmetric matrix, I can write this as 4 outer products of vectors. Okay. So of course there is a way of decomposing these into vector objects. It turns out that it'll be very convenient to think about precisely the special polarizations, E mu nu, where they are literally a bivector of polarizations that had the same structure as the gauge theory polarizations I talked about before. This is me merely building a basis, okay? So in other words, I'm going to think about polarizations that factorize like this, and I have done scattering without loss of generality because I can always take a superposition of any of these to build up a general epsilon mu nu if you want, okay? But this clearly forms a basis, so for each external leg, let me just write its symmetric tensor polarization as a bivector, okay? I can always sum any linear superposition of these to get a general tensor, but I'm going to instead choose this basis because it's a more confined and nice basis to do this analysis. Any questions about that? Okay, so why did I do that? Well, I did that because now I don't have to introduce a new object called epsilon mu nu. I still just have epsilon mu, a single vector polarization. Okay, so this is often a trick that we will use in amplitudes, which is even in studying higher than vector theories, like higher spin than a vector, like a tensor theory, we'll still use vector polarizations as our kind of basis element. Okay. Now let's write that. In fact, this is great. I don't have to do much here. I can actually just erase this. So let's just take this board and we're going to reappropriate it to tensors. Okay. So this is no longer the ansatz. But the structure of the amplitude should look still like a product of polarizations dotted into this. Let me just start over here. So as I just said, E1, I'm sorry, so sometimes I will write E as script E. I should really try to make it consistent. So this is like, this E is the same E. It's not a different E. Okay. This has a subscript. So for E1, E2, and E3, I can write them all as a bivector. So what we have is E1, E1, mu nu, E2, E2, rho sigma, E3, E3, alpha beta, times a whole bunch of junk, mu, nu, rho, sigma, alpha, beta. Okay, so like this is just me really being explicit. This is the form of the object we're trying to sculpt out. Okay. Where I've taken each tensor polarization and split it into bivectors. Okay. So what is the ansatz that we'd write that's made from these objects? Okay, keep in mind these are still the objects that are invariant. These are still the invariant objects that I would have built from vector polarization. So I can use the same basis. Okay. I just want to write a function that is of this form. So what that means is any product of these and sum of products of these, which has two E1s, two E2s, and two E3s. Okay. Let me only write the first couple terms. It turns out this is a 6-dimensional ansatz, but like this would be like terms like E1, E3 squared, P1, E2 squared. Okay, I'll just write, let's say the first two of them so we can see it. E1, E2, E1, E3, P1, E2, P1, E3. And so on, okay, and all the way down to C6. Okay, so let's just look at this first term. There's two E1s, there's two E2s, and there's two E3s. Okay, same for every other term. And I've actually, just like before, assumed the lowest power of p's I can have here, which is order p squared. Okay. I should say, naively, you could have had p to the 0, no momenta whatsoever, like absolutely no momenta. Okay, in fact, let me mention that case. Let's say there's no momenta. This is just a bunch of eta mu nus, a bunch of flat metrics you dot into it. Your whole amplitude is just polarizations dot into each other. Hopefully, it should be clear that you cannot satisfy the Ward identity. Okay. In fact, I should have said this before, but the Ward identity for gravity says, like this. This is what the Ward identity says. It says that, again, I'm not going to review why that is for a graviton, but it's a perfect analog of what happens for Yang-Mills. By the way, if you're interested in all the quantum field theory details of gravity and graviton effective field theory that I haven't talked about, or won't review here, you should look at Matt Schwartz's book, where I believe he talks about Matt Schwartz's quantum field theory in the Standard Model book, where he talks about graviton EFT. Okay. I believe, at least in some version of that book, it was there, yeah, in earlier draft versions. So, so this is a transformation, and the upshot of it is that the gauge symmetry for the graviton is again simply enforced by plugging in E goes to P by the same procedure. Yeah, so the where this comes from is H mu nu goes to H mu nu plus D mu theta nu symmetrized. Okay, so you can think of this as like the analog of like the gauge parameter. Yeah. So in the gauge theory, your gauge parameter is a scalar, a zero form scalar, and its derivative is what you shift the gauge field by. For the spin 2 particle, the gauge parameter is spin 1, and its derivative is what gives you the spin 2 particle. Okay, so that's how it eats the mode. Okay. Now, I'm not going to, well, again, you can look in my TASI lecture notes. I think in the version online, it's in the appendix. I talk exactly about this. Okay. But the point is that we can apply the exact same constraint. We plug this in, solve for the C's, and we get an answer, which is, again, as you can imagine, something kind of nice. Okay, so we'll just jump to the answer. It's a whole bunch of plugging in the equations and solving for the C's, but you understand the mechanics, hopefully, at this point. You want the details? Yes, go to my TASI lectures for the explicit coefficients and so on. But we can then plug back in, and we get an amplitude, which is the following. Okay. E1, E2, P1, E3 minus P2, E3 plus cyclic. Okay, so in other words, exactly what we found was Yang-Mills. Like we found the Yang-Mills factor squared. Okay? So the expression is literally this function, this kinematic function, this was all cyclic, this was cyclic. This function squared. Okay, that is the answer. It has two momenta, two factors of momenta in every term. It is quadratic in every external polarization. And it's also the square of Yang-Mills. Okay. Now, as it turns out, this thing has a name. It's the GR amplitude. Okay, by the GR, I mean the amplitude in Einstein's general relativity. Okay, that is to say, take three of these the gravitons and compute the three-particle vertex in this theory. So you take the metric, plug in, and series expand in H. You'll get H squared terms, which give you the kinetic term. H cubed gives you cubic terms. H to the fourth is quartic. H cubed is a vertex, a Feynman diagram. You can now dot it in with standard rules and compute the amplitude. That's actually a lot of work. That Feynman diagram is like a half a page just for the three-particle amplitude. And you get exactly this on shell. Okay? So the actual Feynman diagram calculation with gravitons is really messy. It's so messy that like very few people even write the vertices. I don't know even in print anyone has written the 5-point vertex. I don't think it's just too big to write. Okay. But here we skipped it by just writing the only thing that was allowed. Okay. Now why? In some ways, there's two things to note. One, we've learned the first appearance of what I called the double copy from last time. Okay. And the double copy structure is the statement that if you take the Yang-Mills answer and take the color and just throw it away. Like take FA, 1A, 2A, 3, just throw it away. Okay, chuck it. We saw before that what we're left with is something that's antisymmetric, which doesn't make any sense because it's a boson. And that's why we introduced F. Well, that said, there's another object that's fully antisymmetric that we have at our disposal, which is this thing in square brackets. This thing is antisymmetric. So what if I just put a second version of it? Two copies will be antisymmetric times another object that's antisymmetric, which is symmetric. That's exactly what happened here. This thing is both-symmetric because it has two copies of that antisymmetric kinematic factor. Okay, so this is kind of the essential way to understand what is happening when people talk about double copy. The idea is to take an expression in a gauge theory or a vector theory, take the coupling constant, which has some antisymmetry properties, some structural properties. Here it's just antisymmetry. Take that structure constant and replace it with a function of momenta, like of kinematical stuff, that has all the same properties as the original structure constant, which in this case happens to be the kinematics. In doing so, you don't just get crap, you get an amplitude in a real theory, which is general relativity. Okay. So that's what the double copy is in like the very simplest version, which is just this. I want to emphasize, though, that in some sense, it was obvious that this was going to be an okay solution because I can always take an object which is Lorentz invariant, satisfies Ward identities, and take it to a power. I could square something and it's still going to be okay, right? If I've told you something's invariant, then that thing squared is invariant. That thing cubed is invariant. Okay, that's essentially what we've done here. We had something that was invariant and I squared it. So we kind of knew this had to be in the solution space. It wouldn't have made sense for it not to be. Okay, any questions about that? All right, so what does this tell us? This tells us that there's no gravity, the only theory of a massless tensor that is cubically self-interacting is gravity, provided I still restrict to order p squared, okay? As usual, that's the stipulation. The only two derivative interacting theory is gravity, okay? But let's keep looking. Maybe there's something more interesting at higher order. Any questions before I look at higher orders in P? Yeah. Good. So that comes not from any internally consistent amplitudes argument, but from the Wigner group and little group analysis of irreducible representations of the Lorentz group. So that is definitely just input. Input into any S matrix bootstrap, you can never get around it, is what the degrees of freedom are. Like you'll never like bootstrap your way into knowing what the spectrum of a theory is. It must be handed to you. In this picture, the fact that massless particles with spin have two helicities in 4 dimensions comes purely from the Wigner classification, which is robust quantum mechanics. You can't derive it. It'd be like deriving in one of the assumptions that goes into it. So it's simply an input. Yeah. Okay. Now let's jump to the next order. Okay. Now I'm going to go faster because I think you get the mechanics of what's happening here. So I can add 2 more derivatives, p to the 4th. Okay. So what that literally means is write down a giant ansatz with 2 E1s, 2 E2s, 2 E3s, and 4 momenta in every possible way made out of these things. Okay. Let me not write it because I think hopefully you get what I'm saying. You find that this thing is actually also unique. Okay? The 4 derivative object you can write is unique. And it is the following. Okay, let me in fact write it. The easiest way to write it is in terms of Yang-Mills. Okay, so in fact, let me just write it this way. Okay. This object that we bootstrapped in a theory of gravitons, the right-hand side is a product of polarizations which factorizes, which beautifully just factorizes, okay? Where the first factor is this Yang-Mills thing in square brackets, okay? There's no color, so this is anything with color structure I've implicitly thrown out from these formulas. But A3 Yang-Mills here, I just mean this function here in polarizations and momenta. And AF cubed is the F cubed thing we computed for Yang-Mills, the F cubed higher dimension operator, that function. Okay, so this is all just E's and P's, but it factorizes. Okay, so that's already kind of amusing. Okay, our building blocks are the same building blocks we saw for vectors, but they're multiplied. Okay. Again, not surprising, given that these are both invariant, so the product should be invariant. Okay, so not surprising. What's maybe slightly more surprising is that the thing that this is in gravity has a name. This is the leading higher derivative correction in gravity. Okay? The leading correction to this thing, which is GB, which means Gauss-Bonnet. Okay, so in this effective field theory, just like any effective field theory, like for pions or anything, the first term is Einstein-Hilbert. Einstein, in his Einstein field equations, wrote down the first term. Okay, but we now understand that there is a sequence of higher derivative corrections, even in gravity, which correct Einstein's equations. Okay, in principle. Okay, like any effective field theory, we should expect those pieces to be there. They are of the form. Okay, let me just write down the types of operators you could have. They could be, for instance, Ricci scalar squared. They could be, let me put like alpha here, plus beta Ricci tensor squared, and then Riemann squared. These all have 4 derivatives. Why do they have 4 derivatives? So roughly speaking, in general relativity, whenever you see a curvature, it's a 2-derivative object. Okay? So since there's two curvatures here, there's 4 derivatives, 4, 4, 4. These are all 4 derivative. That's the 4 derivatives there are these 4 P's. Okay? Now, let's use some things we've learned in the past. Now, I wrote this thing down, and you should kind of immediately be not suspicious, but be reminded of something we saw in the past, which is equations, an action which has equations of motion inside it. Okay, we saw this before for like a scalar field theory. This is like a parenthetical, right? When we had a Lagrangian and it contained a term that like box phi times a bunch of junk. Okay, and we said, oh, we can eliminate this with equations of motion because box phi is an equation of motion. Okay. Well, in these higher derivative pieces, in this graviton effective field theory, Riemann and Ricci scalar, so Ricci scalar and Ricci tensor are in Einstein's equations, right? What are Einstein's equations? R mu nu minus 1/2, R mu nu, let me write it, R mu nu minus 1/2, G mu nu, R equals 0, okay? Vacuum Einstein's equations. So these R's and R mu nus are in the equations of motion, so I can eliminate them by equations of motion. Okay, so in fact, also by taking the trace in vacuum, R equals 0. Okay, so what this tells me is that there is a field basis in the graviton effective field theory where I can eliminate this R squared because it's proportional to the equations of motion. At the level of it's just like the scalar. For the scalar, we eliminate it. In general, it doesn't go away; it goes to some higher point something. Okay. Here, I can eliminate it because there's nothing on the right-hand side of this equation. If I was thinking about gravity with matter, so let's say a gravitational theory where there's matter, then there'd be a stress tensor here, and I could plug this in, and these become stress tensors to various powers, okay? But in pure gravity, I can throw this away, and I can throw this away also, eliminating two of these. So there's like a choice of field basis that these are vanishing, and I'm just left with one, okay? Which is Riemann squared. And I can't eliminate Riemann squared, because Riemann does not show up in the equations of motion. It's where the dynamical graviton actually lives. Now, by the same token that I can drop these completely, I can also set them to any coefficient I want, right? That's like the flip side. When I say that I have box phi times something, I could find a basis where this is 0, but I could also find a basis where this is present with any coefficient I want. Those are the same statement. I could just choose a field basis. It turns out there's a nice particular field basis where I choose this to be 1, this to be -4, and this to be 1, okay, which is known as the Gauss-Bonnet combination. Okay, for various technical reasons, it is an interesting type of higher derivative correction in general relativity. One way of thinking about it is it's the only higher derivative correction you can add in gravity that doesn't introduce ghosts. Like usually when you add more derivatives in a theory, like in the scalar theory, right? If I just added box phi, you're usually in trouble, like in a Lee-Wick type theory or in a theory of with additional modes. These things usually generate new states, and those states have negative norm, and we're in trouble. As it turns out, for gravity, this particular combination of curvature invariance does not introduce a ghost. As it turns out, it's also the combination that shows up always in string theory in low energies. Okay, so the consistent theories tend to spit this out in low energies, okay? As you should expect. This was all a long story to emphasize that this here is called the Gauss-Bonnet term, Gauss-Bonnet. Okay, and it is exactly this product. And if you just did that crazy hard work of computing the Feynman diagram the hard way, you would just find this expression on shell. Okay, so this again is a shortcut to even studying the higher derivative corrections in gravity. Okay, any questions about that? Yes. Right. Well, I mean, maybe the way I'd say it is, when people do write this and include these terms, and they were about ghosts, like this would happen, for instance, in stellar gravity, they would keep these coefficients here, and they never think about it in an effective field theory context. So in an effective field theory context, when I see R squared and R mu nu, they're corrections to the leading piece, and thus I can remove them with a field redefinition because they're subleading the FT. In the cases where these are present and people have those ghosts, they're always in a regime where this is as important as the leading term. Okay, so for instance, in the cosmologies where this actually matters, this is not subleading in any sense. It's as important, and those degrees of freedom come, and then you're in trouble. So in some sense, the way I would really say it is that like the amplitudes is like really strongly hewn to the effective field theory picture, where these are corrections. These are distinctly corrections. Yes. Yeah, it's almost like it will always be okay. See, if you have an effective field theory, you know your late degrees of freedom. There could be maybe modes at the cutoff that are ghosts, but in EFT, you're never plagued by that because your mode is a graviton that just couples with nonlinearities. So an effective field theory perspective doesn't see those ghosts. They're at the cutoff and they're not in the validity of EFT. Let me mention one more thing because this is actually related to one of the weird miracles that's hard to see in amplitudes, but much easier to see in field theory, which has to do with the fact I mentioned previously last lecture, which is that gravity is curiously, in some ways, more UV finite than gauge theory. Okay, it sounds like the exact opposite of what you're used to, but that's true. This is what I mean by that. If you take Yang-Mills theory, of course, it has a beta function and it has running log divergences at one loop. It's divergent at one loop. Okay, you add counter terms and then you have log divergence, which generate the beta function. What about gravity at one loop? So super famously, this was computed by Tufte and Veltman like super long ago. They just took gravity and then computed loops in that theory. Okay? Now, just like in any effective field theory, because of the derivatives, the more particles you close in a loop, you get divergences, but they correct higher derivative pieces. So this happens in, for instance, the chiral Lagrangian. The first loop in the chiral Lagrangian renormalizes a higher derivative term in the chiral Lagrangian. Okay, it's just a fact about momenta. These momenta stack up so that when you put more vertices with more momenta, you renormalize operators with even more momenta. Okay, that's just the way effective field theories like this work. And that's why when you compute one loop divergences in gravity, you generate infinities for these terms. Okay. Now, in general dimensions, that is fine, and it's divergent. Okay. But as it turns out in 4D, there's something special about Gauss-Bonnet. 4 dimensions, specifically 4 dimensions, something magical happens, which is that Gauss-Bonnet is a total derivative. Okay? So it turns out this precise combination, that is to say, the final combination that could have done anything, is a total derivative and doesn't affect any dynamics, which means that you can eliminate all these terms entirely, which is precisely why gravity is actually a finite theory at one loop. It's finite. It's so well behaved, it's finite, calculably finite at one loop. Okay. Now, of course, at two loop, people immediately wanted to go to two loop. Very hard calculation, even with modern tools. It's not finite at two loop. The divergence shows up at two loop. But curiously, it was better behaved than you thought. Now that said, I want to return to this because what I just said should have confused at least some of you, because I just said this is the total derivative. And in 4D, in 4 dimensions, and you might say, wait a minute, what does this mean? You just told me that that's its amplitude. That's not zero. That's not a total derivative. Okay. And here's why that's consistent. Our analysis here never made mention to dimension. This is the expression in arbitrary dimension. In like 17, 26, 10 dimensions, 4 dimensions, this is true. Specifically in the case of 4 dimensions, this actually vanishes. Okay? Now you might be confused. Like, how can it vanish? Like, Yang-Mills is not 0 in 4 dimensions. F cubed isn't 0 in 4 dimensions. How could they vanish? We'll see the reason when we go to spin helicity, but I'll just, a spoiler, tell you. For the choice of helicities, where A Yang-Mills isn't 0, AF cubed is 0, and vice versa. In other words, there's a label in 4D, which is helicity. It's buried inside these polarizations, and you can't make both of these non-zero at the same time in 4D. That's the resolution. We'll see that very explicitly again when we do spin helicity, which is the kind of next way I'll study this. But the point here is that in general dimension, this is robust. Okay. This is also, as you can see, a version of the double copy. This may be not the right word to use here because it's not the same factor twice. Up here for gravity, it was the same Yang-Mills factor twice, but now it's 2 different factors. But that's because when people say double copy, they mean this general operation of taking products. It doesn't have to be a perfect square. It can be 2 products of different things. One easy way to understand also why this thing was allowed, again, was to return to the Yang-Mills story. Right? The Yang-Mills, I told you this thing was antisymmetric. I need to put some blob here that's also antisymmetric, so I put a structure constant. One option was, instead of the structure constant, put another factor of this. But there was another option, which is to put a factor of AF cubed, which was also antisymmetric. That's the point. Like, I've just replaced the structure constant with another function, which was AF cubed. That's all I'm doing, is mixing and matching. Okay. With that said, you can probably anticipate the last kind of bullet, okay, which is order p to the 6th. Okay, I have 6 momenta. Again, this is all proportional. This, as it turns out, and very unsurprisingly, is f cubed squared. It's 2 factors of the AF cubed. Okay? This thing, each A3F cubed has 3 momenta. I square it, so I have 6 momenta. So that's the 6 momenta. Okay. Yes? So it couldn't have been, that's a good question. It could not have been Yang-Mills cubed because Yang-Mills has 1 polarization in each, like E1 shows up 1 time in A Yang-Mills. So 3 of them would give you a 3 tensor, like a 3 index E1, but we only want a 2 index one. But it's very good. What you're suggesting is not a double copy, but a triple copy. Okay, that's a very fair question. You could say, why am I stopping at just these simple products? Okay, why couldn't I take A Yang-Mills to the 20th power? Like literally take A Yang-Mills to the 20th power. What's wrong with that? Okay, that's as invariant as A Yang-Mills. It's fully symmetric because 20 is an even number. As it turns out, that is in fact the 3-particle amplitude for a massless spin 20 particle. That's also what it is. So if you wanted to go to higher spin, you could do it. Now, famously, massless higher spin particles those theories are hard to formulate. At 3-particle scattering, they're not hard to formulate. You just literally take products like this. The place where they start dying and not existing and being inconsistent with principles is 4-point and higher, which I haven't yet gotten to. Yeah. But indeed, you can imagine doing this beyond 2. Okay, now sorry, I didn't get to what this is. This also has a name in GR. This is R cubed, which is yet another correction to gravity, which is, as you can imagine, just the next one, which is R mu nu rho sigma cubed. The cubic Riemann object. Yes? Right, right. I would say it's obscured, right? If you didn't make a more general basis choice, if you used a more general basis choice, it would be like taking sums of these, right? Because any general tensor is a sum of them, and it would obscure it. So if you like, there has been some cleverness or like wisdom in the way I've chosen to parameterize to make it manifest. That the basis elements of these tensors has this square structure. So it did take some insight, but this is a basis, so I can build anything from this. And what that means is that when we calculate, this tells us the basis we should calculate. It's the basis in which our polarizations are bivectors. Okay, very good. So this was R cubed, Riemann cubed, and what does this tell us? Again, so we could go one order higher, but now you know what the game is. So if we had p to the 8th, it's 0. Why is it 0? Well, if I give you 3 polarizations, that's a total of 6 of these e's. That's 6 indices. There's 8 p's, so 2 to the p's contract, so it's 0. Okay, so there's nothing else. It's plus. There's no other 3-point coupling. This is only 3-particle amplitudes that can affect gravity. That can be, well, that can define a theory of massless spin 2 particles. Okay. So what we've learned? We've derived the uniqueness of general relativity, at least in terms of 3-particle amplitudes. Okay, we'll get to higher point a bit later. We've derived the uniqueness of GR purely from what? Lorentz invariance and the fact that we have a massless spin 2 particle that is interacting with itself at 3-point. Okay. Now, of course, you are probably maybe aware that there's a huge wilderness of modified versions of gravity that people talk about. For instance, massive gravity, Mond, TV, scalar modifications, Brans-Dicke, whole litany of them, and they're not this. So what does that mean? It means that they break a rule. One of the rules we assumed they broke. So some of them just aren't unitary, some of them are sick. But in the vast majority, at least in the responsible types of modifications, there's just another degree of freedom. Okay? We assumed it was only gravitons. If there was also a scalar in play, then we could get a scalar tensor type theory. If that scalar mode happens to be the longitudinal mode of the graviton, then it's massive gravity. Okay? And that's just a different analysis. We assumed massless. Let me just point one thing out, because this is actually not super well known, but I find it kind of interesting. There's actually another option that no one talks about, which is not any of these kind of exotic formulations, which still has only a massless graviton in the infrared, but isn't GR. It's a less well-known paper by, at least best studied by Kurt Hinterbichler, called pseudo-linear gravity. And it's maybe too much to jump into here, but it's kind of interesting. But the way it gets around it is it doesn't have the 3-point vertex. It starts at higher point. So the way it slickly sidesteps is it doesn't have a long-range force mediated by 3-point. Its first vertex is at 4-point. Yeah. But it's, if you like, a perfectly fine, at least from these principles, theory. Okay, good. Any questions about any of this? All right, so everything I've done here has still been 3-point. 3-point is not impressive, but it should tell you how much Lorentz invariance has dictated the rigidity of the theories we study. Okay, so next time someone says the beauty of gauge symmetry, GR, elevators, what a beautiful story. You can also know in the back of your mind that that's all fine and true, but it's also couldn't have been another way. It's not like there was an uglier version of GR. Like, this is what was mandated. As soon as we said massless spin 2 with a cubic interaction, it was GR. Okay. Now, to go to higher point, we can actually keep going with this bootstrap with these objects. Maybe I can mention just quickly what that would like structurally look like, but then really dive into a cleaner way of doing it, which uses so-called spinor helicity, which you've seen. But let me just mention it, okay? Which is, in fact, I think the kind of one of the nicest places where this was done was in a paper by Nima Arkani Hamed. But you can actually do this by, you can do an analysis like this, okay? So if you think about a Yang-Mills amplitude, it has various poles, and it has various numerators. Let me just write it schematically, okay? The idea is to imagine an ansatz for the amplitude, which is a numerator over a denominator. The denominator has to be all possible poles that the amplitude can have. So like poles in the S and T channel and so on, okay? The numerator is any slop that's made of E and P, okay? Now, the size of that ansatz depends on how many derivatives you want. Okay, so if you say I allow for an infinite number of derivatives, obviously you'll have a huge infinite ansatz. But if you say I only want things with 2 derivatives total, then it fixes how big this function can be. And then for this object, you then enforce these word identity constraints. Okay, so this is a cool paper that I recommend. It's very interesting by Yaroslav Trinka and Nima Arkani Hamed. It's called Gauge Symmetry and Gauge Symmetry and Locality, Fixing Scattering Amplitudes. But it's this kind of basic bootstrap. But I'm not going to pursue that here because I think it's kind of cleaner and at least closer to how most people think about amplitudes to shift gears to a better set of variables, which are spinor helicity. Okay. Any questions about this before I kind of shift gears to that? Actually, first of all, let me poll the audience. So I want to talk about spinor helicity, but I don't know how much I should review or kind of view as already being reviewed. Do you want me to jump in the middle, or do you want me to pretend that you've never seen spinor helicity before? So who wants me to pretend you've never seen spinor helicity before? Oh, good. Almost no one. Okay. Who wants me to jump like in the middle? Okay, jump in the middle. Okay. Who wants me to jump right to the end? Okay, no one. No. Okay, okay. Definitely, there's hard boundary between like the end and the middle here. Okay. So why don't I flesh out just my conventions? Okay, and then show you some things. Okay, but it'll be mainly my way of moving into something called on-shell recursion, which is a very crisp way of getting to higher point from lower point. Okay, but let me start with spinor helicity. Okay, and I guess since you've seen it so many times, I'm going to just present it in a way that you can know what my notation is. Okay, so here's my conventions: spinor helicity. Okay. So I won't be like necessarily, I will attempt to jump to the middle, but let me tell you my convention. So the idea of spinor helicity is it is a formalism for describing kinematics in 4 dimensions, okay, specifically 4 dimensions, and it hinges on nice properties of the Lorentz group in 4D. Now let me just mention, the basic picture here has been generalized beyond 4D. There exists spinor helicity 3D, 5D, 6D, 10D, okay? And just there are many like variations on a theme here for spinor helicity. It's kind of the starting point for many other different ways of representing momenta. In the end, all it is taking P1, P2, P3, P4 and like reconstituting them in some other way. But remarkably, depending on how you do that, you can find immense simplicity and structure fall out if you just write it the correct way. Okay, that's maybe a little surprising, but it's true. Okay, so what is my notation? So notation is, well, let's say we have some P mu, okay, 4 vector, which is going to be on shell. So our external momenta are going to be on shell. The basic idea of spinor helicity is to make P squared equals 0 hard-coded into your formalism. I don't have to like keep imposing it as a constraint or working hard to fix it. I want variables that have no choice but to live on the on-shell surface, the on-shell space. Okay. So to do that, we write P mu alpha alpha dot, where this is the usual Pauli matrix. I can define this as P alpha alpha dot. And again, just so we have fixed conventions, I'm defining this as P0 plus P3. And this will differ from other conventions, but this is the one that I am using. This is a 2 by 2 matrix, P1 plus I, P2, P0 minus P3. Okay, it's like super explicitly in terms of components. And the point is that if you take the determinant of this P alpha alpha dot, okay, it's a 2 by 2 matrix, you take its determinant, it equals P mu, P mu. Okay? What does that mean? It means there's a 2 by 2 matrix whose determinant is vanishing. That means one of its eigenvalues is 0. Okay, so it has the apparatus has 2 eigenvalues, one of them is 0. If something has 1, 0 eigenvalue, then it can be written as the outer product of a single outer product of spinors. So in particular, P alpha alpha dot equals an outer product of two spinors, which I'll call lambda and lambda tilde alpha dot. Okay, so this is just a two-component object. It's another two-component object. And since P has vanishing determinant, I can always write it this way. Okay? Anything with vanishing determinant can be written this way. So I've assumed nothing. Okay? These lambdas and lambda tildes are called spinor helicity variables. These are the kind of sometimes called angle and square spinors for reasons that will become clear. That reason is that we can build inner products out of these things. Okay, so for this construction applies to each external leg. So each external leg will have some pi equals lambda I tilde. So hyper concrete pi. So leg I has one of these, and it equals lambda I alpha dot tilde. Okay, and my inner products are defined in the following way. These are the ij's and square ij's I read before. Okay, angle ij, square ij, which are just the invariant products built out of these. Okay, alpha and alpha dot are spinor indices. The Lorentz group, so their natural inner products are lambda I alpha, lambda j beta. Okay, epsilon alpha beta. Well, this is lambda I alpha dot tilde lambda j beta dot tilde epsilon alpha dot beta dot. Okay, so it's just the anti-symmetric products of these things, contracted with an epsilon tensor. Okay. So anytime you see an angle bracket or a square bracket, it is a Lorentz invariant. Okay, when I wrote those expressions for what I called the Park-Taylor formula and so on earlier, all those angle and square brackets are just these. Okay. So the big picture is every momenta has been factorized. We've taken its square root into two more primordial objects, and then we write every amplitude in terms of inner products of those objects. Okay? Sorry, what was the question? What is? Oh, epsilon, let's see. It won't matter for what I'm saying, but you're asking about literally the sign convention. So I think maybe 1, 2 equals plus 1. But there's no way that my resolution for what I'm going to tell you is going to care about that. But let's take that as usual. For any Levi-Civita permutation symbol, properly ordered as plus 1. Yeah. That can change, of course, if you switch from Euclidean to Lorentz. There's all these like other fine signs that I'm not worrying about. But yeah, let's just pick that convention. Good. And the essential only identity that you need to know, since these are two vectors, is the fact that any three two-dimensional vectors are linearly dependent, right? In a two-dimensional space, any three two-dimensional vectors are linearly independent. And that identity has a name. It's called the Schouten identity. And it looks like this. It says if I have lambda I, lambda j, lambda k, then this particular combination of these is 0. Okay, so lambda I, lambda j, lambda k are all two vectors, and this particular weighted sum of them is 0. That's the linear dependence amongst them. Okay? What does this let you do? It lets you exchange lambdas for other lambdas. Okay, and it's a freedom that's maybe a little bit, the spiritual cousin of like momentum conservation. It's some kinematic thing. I mean, at least practically, like mechanically, it's something which will let us rearrange amplitudes in various ways. Just like I could eliminate P3 for everyone else, P1 plus P2. I could eliminate lambda k for lambda I and lambda j in this way. Many ways of rearranging terms. Okay. Now, before like calculating or doing things with this, let me just show you like why something nice happens in many theories. So probably the best example is the Park-Taylor formula, which I mentioned before. The story for this is actually pretty amusing. So I don't know if you've heard this story maybe in previous lectures. Did you hear the story of Park-Taylor? Like the legend of Park-Taylor? No? Yeah, it's great. It's great. It's not folklore. It's actually really happened. It's kind of amazing. So back in long time ago when people were still trying to understand relatively low-level facts and calculations in gauge theory, Park and Taylor were interested in the scattering of gluons, and they computed at 5 and 6 point these, I believe, up to 6 point, the 6 gluon amplitude that I mentioned before in Feynman diagrams. It was like brutal, many, many pages. And kind of brilliantly in their original papers, they had these like very mysterious comments about how, this is pretty ugly, but we strongly suspect that there's a much simpler version of it, okay? And in their next set of papers, they wrote down what's called the Park-Taylor formula, which was the compactification of those like hundreds of terms down to a formula for 6, 7, and n point scattering amplitudes with certain helicity combinations, which is the Park-Taylor formula. So there's kind of it's almost like the dream of most amplitudes people, which is like find something crazy complicated and learn that it's really simple. I had written this down before, but let me write it again. What is the amplitude in question? So let's say you're in Yang-Mills theory or gauge theory, you're scattering gluons. But let me have n gluons, okay? So we're immediately jumping from 3 to like a huge number, okay? 50,000 gluons, okay? But let me imagine that all of them have plus helicity. Almost all of them have plus helicity, except for 2. Okay, so like there's a whole bunch, n minus 1 plus, okay, so this is my notation for this amplitude where each number here is one of the legs, and I'm putting a superscript to tell you what its helicity is. Because in 4 dimensions, everything's labeled by helicity. So these guys are all plus helicity, these are all minus helicity. In fact, everyone's plus and minus, except for, everyone's plus, except for 2 legs, which I'll call I and J, which are minus. Okay, so you just imagine like all plus, every single external leg is a plus helicity, except for 2 legs, which are I and J, which are one of the legs, 2 of the legs, and they have a minus helicity. So it turns out that this amplitude has an unbelievably simple form in terms of these variables, which is an ij to the 4th corresponding to those 2 special legs, divided by an awesomely cyclic structure, 3, 4, like all the way out to n minus 1, n, and 1. Okay, everything's angle brackets. So lambda tilde disappeared. It does not show up in this amplitude. You don't need it. You can write it purely in terms of the angle brackets. Okay, this is true for n particle scattering. It's kind of insanity if you think about like how simple this is and how crazy hard an actual calculation would be. So for those who rightly like ask like, is there like a practical advantage? I mean, you should do this. As an exercise, compute the 8 particle gluon amplitude with Feynman diagrams. Okay, step 1. And then by I, simplify it to this formula. Okay? You don't get to use numerics. You have to do it analytically on paper. Okay. So you could do that, of course. I sadly have those amplitudes that you could even check this. But of course, there is a way of getting this more directly. And the way to get more directly is to not start from Feynman diagrams at all, but to start only with expressions like this and build them from other expressions like this, okay? Which is what I'll get to. This is true for gauge theory. So this was Yang-Mills. There's also a formula like this for gravity. Okay, so if 8-point gluon scared you, 8-point graviton should like give you nightmares. Like I don't think I know anyone other than me and maybe some collaborators I know who've gone above like 5-point for graviton scattering. It's so crazy. I think 6-point didn't fit on my computer. Like you could have it run, but it's just so big and ridiculous. Why? Because even writing the vertex takes memory and then contracting them all possible ways, it's crazy. Okay, so as I said before, the 4 particle graviton amplitude is around 100 kilobytes. But for GR, you can do the exact same configuration, which is everyone's plus, okay, except for one. So I'm actually going to put 2 pluses here for leg 1 and 2 pluses, and I'm just doing that to kind of emphasize that these are spin 2. Like that's the only reason I'm doing this is to emphasize. This is vector, helicity plus 1, helicity minus 1. This is helicity plus 2 until you reach I, which is helicity minus 2, and helicity j minus 2, and so on. Okay? But the point is everyone is plus, except for 2 legs. So this could be like literally a bunch of gravitons, and then 2 are special gravitons. Okay? This also has a formula, which is unbelievably simple, written down, it was 2006, relatively recently. Again, just by kind of brilliant guesswork by a genius named Andrew Hodges. And Hodges, this is known as the Hodges formula, showed, okay, so let me be slightly schematic because there's some prefactors, that this is essentially equal to the determinant of a matrix where the entries are dictated by phase factors. So it's a matrix where the rows and columns are A and B. So just build a matrix out of this and then take its determinant. Okay, that's the formula for n gravitons. Up modulo some prefactors, which I don't want to have to write out because they're messy. Okay, but just simple prefactor. Okay. What's that? The ij's in the prefactor. There's some ij to the 8th in front, and then yeah, that's based. I didn't write it, but there's an ij to the 8th in front. Yeah. This is called the Hodges formula. So this is Park-Taylor here, and this is Hodges. Okay. Again, why is it true? Well, you can check it. So these are known facts that are true. But like, why? Like, why does a beautiful formula like this exist? Does a formula exist like this outside of this context with more minuses? Okay. Open questions. Like, it's like, we don't know. We have no idea. But this is exactly, at least to me, the spirit of like why Amplitudes is fun. Like you encounter things like this. What you normally call just an absolute miracle. There's reasons to argue for this that are relatively straightforward. Like you could reason through this using things called collinear singularities and understanding pole structure. But this formula is true, at least to me, like more magical. It could still be kind of deduced, but it's pretty magical. Okay. So I want to claim first that this thing is extremely simple. It makes things that are impossible to write, I would say like quite literally impossible to write by other means, and puts them in a compact expression. Now, that all said, let's actually bootstrap with this thing, okay? And this is me now cutting to the middle, so to speak. Okay, because actually, let me ask. So did the previous lecturers show already the uniqueness of the 3-particle amplitude with spinor helicity? So with spinor helicity variables, you can show and write down a closed formula for every 3-particle amplitude. Did they cover that? Okay, I'm not seeing recognition. So if they did, you don't remember it. Yeah, okay. That's okay. Do you want me to, I should probably cover that because it's part of the bootstrap. Let me cover it. Okay, let me say it. So I'm not going to be jumping right in the middle. Maybe this is jumping in the middle, but this is just what the definition is. Let's use it. Did other folks talk about the little group? Yeah, okay. You know the little group. Good. All right, good. So again, just to recap my conventions, under the little group, it's a statement that we can take lambda and lambda tilde for some external leg. And we can rescale them. Okay, so like in an expression like this, for instance, you could take lambda 1, okay, and you can take lambda 1 and rescale lambda 1 by t1. And take lambda 1 tilde and rescale it by t1 inverse. Okay, you could just like do that operation here. Okay, and what you'll find in all these amplitudes, in every physical amplitude, is that some power of t factors out. Okay, and that power of t dictates the spin of the particle in play. Okay, so like let's be like kind of concrete here. In the case of Yang-Mills, let's say I take, let's imagine I and j is somewhere deep inside here. I and j are like 27 and 59. Okay. Let's look at particles 2 and 3. Okay, so we take angle bracket 2. Okay, so we take angle bracket 2, lambda 2. We send it to lambda 2 t2. We take lambda 2 tilde, send it to lambda 2 tilde t2 inverse. Okay, there's no lambda 2 there's no tildes anywhere, so I just have the top line. That just rescales this lambda 2, this 2 and this 2. It gives me a factor of 1 on T2 squared, okay? That tells me the particle in question had helicity. The factor, the powers of T that come out tell me the helicity of the leg in question, which was helicity plus 2. Okay, so you said that you saw a little group, so presumably that is a review, which is to say that if you take an amplitude, let me write it out more formally, where I have helicities, abstract helicities, H1, H2, all the way to NHN, sorry. Okay, where H1 could be plus 1 or minus 1, H2 could be plus 1 or minus 1. Then under the little group, this thing transforms to the same amplitude, but times a factor of Ti to the minus 2Hi. Okay. So there's a homogeneity property of amplitudes. When you rescale spinors, they factor out. That rescaling factor is out, and the power of the factor that comes out actually tells you the helicity of the particle in play. Okay, so again, yeah, if this was 1, plus 1, and minus 1, then you get a T1 to the minus 2 and a T2 to the plus 2. Okay. If you had spin that's very large, very high helicities, very large spin particles, then these factors get bigger. Okay? But this is, if you like, what is called the little group constraint on the amplitude. These amplitudes all satisfy this property, okay? As they should by consistency. Okay, questions about that? Okay, now we can use this to write down the 3 particle amplitudes, every 3 particle amplitude for massless particles in 4 dimensions, in a single formula, which I guess you haven't seen yet. So this will be kind of cute. Okay, so this property alone is enough to fix 3 particle scattering once and for all with the formula. Okay, and it will encode all the formulas we saw at 3-point, like as a corollary. Okay, and it's a pretty nice formula. But let's work it out. Okay, so we'll start with 3 particle amplitudes in the spinor helicity type bootstrap. So noticeably, in the previous section, I had to start with scalars, vectors, tensors. I kind of work my way up with different spins. Here, we're going to take it all at once and do arbitrary spin. Okay, we're going to just do every spin all at once because it's much easier. And we're going to start with 3 particle because it's where the action starts. So 3 particle. Okay. So what do we want to do? Well, we want to do the same thing as usual. We want to write a function A3 that depends on angle brackets and square brackets. Okay, that's all we want. It's a new space of kinematic functions, not P dot E and E dot E and P dot P, but just angle and square brackets. Okay? But let's think a bit. Okay, so let's think a bit more. So let's think about kinematics first. Okay, so P1 plus P2 plus P3 equals 0. Okay, that's the momentum constraint. Keep in mind that since we're representing momenta as 2 by 2 matrices, right? We have those alpha and alpha dot matrices. This is a 2 by 2 matrix plus another 2 by 2 matrix plus another 2 by 2 matrix is 0. Okay, so everything here is in spinor helicity. Okay. But let's calculate. So let's say we took P1 plus P2 squared, which of course we know is P3 squared. Sorry, this is P3 squared. Okay. When I square this thing, I get 2 times P1 dot P2. Which in my normalization, if you, again, this is hopefully something you've seen because you've calculated, this is going to be 1, 2, 1, 2. Okay? So this is just the expression you get. So I'm saying literally if you take the 2 by 2 matrix, P1, add to it the 2 by 2 matrix P2, that's a new 2 by 2 matrix, then take the determinant, because that's how you take an inner product, you'll just get this. Okay? I'll just leave it as an exercise. More generally, you can take anything else. You can take P2 plus P3, which is P1 squared. And this is going to be 2, 3, 2, 3. And lastly, P3 plus P1 squared, which is P2 squared, equals 3, 1, 3, 1. Right? And all of these are 0, because this is 0, and this is 0. These are all 0. They're all 0. Because P1 squared, P2 squared, P3 squared is 0. Okay? In other words, this quantity is 0, this is 0, and this is 0. Okay. Now you might think, oh no, we're in trouble. These are all 0. The amplitude's 0. What's happening? Okay. And in fact, in real kinematics, it would be 0. That is to say, if your momenta are, hopefully this was also told to you in the past, but if your momenta are real momenta, then lambda tilde and lambda are related by complex conjugation. But for complex momenta, they're free. Okay? So the way we think about this in amplitudes, as usual in an S matrix, is that everything's complexified. We think about everything as a function in full complex plane, and then we want to compare against experimental data, we return to the complex plane. But we can still classify things in the general complex plane. Which means that these vanishing doesn't mean they're all 0, it just means that one of the factors is 0. So, for instance, let me assume that 1, 2 is not equal to 0. Okay? If 1, 2 is not equal to 0, then this implies that the other 1, 2 square bracket is 0. Okay? Now I can, let me try to wrap this. Well, let me finish with this and then I'll wrap. So as it turns out, this implies. Let me kind of skip the algebra. If you keep plugging these in sequentially into each equation and use momentum conservation, you find that 1, 2 is 0, 2, 3 is 0, and 3, 1 is 0. They're all 0. Okay? Which simply means that lambda 1 tilde is proportional to lambda 2 tilde, which is proportional to lambda 3 tilde. Okay? When a bracket vanishes, it just means that two spinners are parallel, right? Because it's an antisymmetric product. So in other words, when this is 0, it just means 1 and 2 are pointing in the same direction, which is why it's vanishing. So this is one branch of solution, which is just that these lambdas are parallel to each other. There's another branch where lambda is proportional to lambda 2 is proportional to lambda 3. Okay, so there's two branches. In one branch, these are all parallel, but the lambdas are unfixed. In this branch, it's the opposite. These are all parallel, but the lambda tildes are unfixed. What that means is that we have two branches of solutions. We have a branch of solution that depends only on angle because the squares vanish, or a branch where the opposite is true. It only depends on square brackets because the angle brackets vanish. Okay? Which means that we have a completely general ansatz now for the amplitude, which is, and I'll stop here and then we'll finish next time, which is that A3 is either a function of only angle brackets or it's a function only of square brackets. Okay? And what we'll find next time is that we can entirely uniquely fix these functions at all orders in perturbation theory and classify all 3-point amplitudes of massless particles. I should also maybe note that the case of massive has also been studied and worked out fully, so the entire 3-particle space of all possibilities is just known, completely fixed, and we know that nothing is missing. Yes, question? Different branches correspond to different physical configurations of helicities. In fact, I'll just tell you, roughly speaking, the sum of all your helicities will dictate whether you're in this branch or the other branch. Okay, so like plus 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 will be in like this branch and minus 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 will be in the other branch. That's where they split. So both branches are fine. They both are exhibited in nature. And in fact, chirality, flipping left and right, will move you between the two. Yeah, but we'll see very explicitly that, especially since I guess you haven't seen it previously. Any questions? Any more questions? We can talk more in the discussion, actually. Maybe we can just clean up much of this stuff. That's all. Thank you.